Demetrius has framed this topic for today's lecture in the context of the past, meaning not only the historical past, but also the more distant paleoclimate past. Demetrius spent a ton of time in his PhD working on just putting together historical data records to try to say something robust about drought variability over the last few decades. And those two pieces of evidence, the past and the present, or the 20th century, give us insight into the pace and the magnitude of climate change projections. They give some context for the climate change projections when we look out past, say, 2050 or to the end of the century. And it lets us assess whether or not the scale of changes that are projected to occur are outside or well outside the range of what's been experienced recently or in the distant past, and what some of the impacts might have been in the distant past, including potentially the demise of some pre-industrial civilizations. So this is how I think of most climate problems in this context, and the Caribbean is certainly no exception. But just to kick things off, we did this with Demetrius' PhD defense. We just asked the audience, one word. What's the first word, first image that comes to mind when you hear the Caribbean?
Beaches.
We've met before. Beaches, yes.
Rum.
Rum, okay. Awesome. Yeah, stood up over here on this side. First word.
Seawater.
Small islands.
Whoa, feedback. Okay, so I have to stay on this side of the mic for the speakers. Otherwise bad things happen. Okay. Feedbacks are scientifically interesting.
Coral reefs.
Coral reefs, all right. I don't have slides for all of these things. Some of them, yes. What about, something else?
Rush.
Storms, yes, thank you. Good. All right. Yes, tropical meteorology. Appreciate that. Yeah, so those are kind of that's a very similar conversation that we had right before Demetrius' talk. We're talking about this little red box there. This is a map just sort of to orient all of us, make sure that we're on the same page in terms of we're really focusing today on the Caribbean. However, Demetrius' work has extended the approach to most of Central and South America, and the northern part of South America, and even the southern part of the U.S. So if any of this is interesting to you, or you're working on projects in any of those regions, talk to Demetrius, talk to me, because we have data sets and we're working on a number of applied data products that could be potentially useful to your own research. All right, so we talked about the beautiful beaches. Some people said cruises. This is where we wish we were today. Sailing, right? People go down this time of year and sail for a few weeks in the Caribbean and the Bahamas. Certainly tropical storms, hurricanes are a big deal there. And then this came up. Someone said this in Demetrius' talk. Pirates, the first thing they think of. Pirates of the Caribbean, if they've been to Disneyland recently or seen the movie recently. But this is in the Caribbean. And this is a picture that Demetrius took from your father's farm, right? Yeah. So this, we showed this and we asked people, where do you think this is? And half the audience, when we did this, said, no, it could be like New Mexico, right? This is a much more arid landscape than we're used to thinking about when we have this image of the Caribbean being just this luxurious green vegetation with palm trees and beaches. But there's also dry areas, and in addition to there being dry areas in the Caribbean, there's also droughts, which is what we're going to focus on here. So this is San Juan. It's in the southwest part of the Dominican Republic. And just to give you some scale estimates here, there's a lot of people living on a relatively small area, about the size of Oregon. And that's going to become critically important when we think about climate change impacts. And the first thing when most people think about climate change impacts in the Caribbean is probably sea level rise. Perfectly fair point. However, sea level rise combined with drought is especially challenging. It's an especially challenging obstacle because you have many freshwater aquifers that are fueling agricultural systems that are already being contaminated by saltwater intrusion from overpumping and a tiny bit of sea level rise that we've seen so far. So you put sea level rise together with droughts and increased stresses on aquifers in the future, and you have new, what we would call in my lab, emergent risks. And so I'll hopefully leave some time to talk about that and think a little bit about, with you. I'm not an expert on adaptation strategies, but certainly being aware of those risks is an important first step to being able to manage them as we move into the future. So paper that this came from, there were two papers that came out back to back in very high-profile journals, and they looked at among other things the most water-stressed countries in the world, and 7 out of the 36, so almost a quarter of the most water-stressed countries in the world are right here, right in our, right to the south of the coast in the U.S. And I just mentioned this, and I'll show you what I'm talking about here. And I think when we went through this last drought that occurred in the Caribbean, which motivated a lot of Demetrius' work from 2013 to 2016, it's probably not an exaggeration to say that had it continued another maybe 6 months or a year, the stresses to human life and agriculture and systems on these islands would have started to provoke much more serious humanitarian crises and refugee situations like we're seeing in other parts of the world. It didn't happen. In fact, the drought was ended by a hurricane, right? So a hurricane season ends the drought. So it's a very extreme regime to be living in. It's a very extreme setting to go through a 3-year drought, which is really challenging the water resources, and then have extreme weather hurricanes be the thing that brings the rainfall that ends the drought. But just to give you a mental model for what the freshwater picture looks like, you have rainfall that's recharging what are usually these freshwater lenses, especially on the smaller islands. And then you have the ocean on either side, and once you pump out that water, you reduce the outflow, you reduce the pressure that's holding the salt water at bay, and so now you allow for saltwater intrusion. In addition to that, you have the potential for sea level rise and storm surges as well, which can contaminate the aquifers. So let's look at the one example that I think probably a lot of people would be familiar with. It's often cites, it's become a popular science term almost. Mega drought, the Mayan mega drought, the multi-decadal mega drought that may have been linked to the demise of the Mayan civilization, among other factors, several hundreds of years ago, several centuries ago. And it seems like it probably did also affect the Caribbean region, that whole entire region was drier on average for multiple decades at a time. And so one of the features of the paleoclimate past, the records that we have from the past, is that it lets us treat individual centuries or multiple centuries as a handful of samples. So when I say paleoclimate, let's do another little Q&A with the audience. What's like someone in the back, like paleoclimate, like what's the first thing that you think of when you hear about paleoclimate records? What do you think it's just in a general sense, not necessarily specific to the Caribbean, but in a general sense, what's going to be available? Yes?
You can look at trees and like really old trees, and you can trace the climate back thousands of years.
Right. Does that make sense, everybody? Trees are a nice, what we call like a paleoclimate proxy for historic variation. So that turns out not to work super well in the tropics in general, and in the Caribbean in particular, because the annual growth rings on trees tend to be a feature of boreal forests that have a warm season and a growing season and a dry season and a wet season. So in the Caribbean, the rings that are on trees are not necessarily annual. So there's just we're working on trying to get some samples. Like Demetrius is going in like March to try to find some sites that might have annual rings. What other paleoclimate proxies? So we say paleoclimate proxies, we're talking about going back in the past for hundreds of years, or even millennia, to get climate information. What else? What's that? Ice cores, yeah, certainly ice cores for other parts of the tropics. Further south in the Andes, we've got ice cores.
Soil and rock records.
Soil and rock records, and that's definitely an important component of our paleoclimate toolkit. The soil and rock records tend to be coarse resolution in the sense that you might have one sample that's representative of a long period of time. What else? Anything else? Just two more important ones we haven't talked about, which we're going to show a little bit from.
You look at pollen and mud.
Pollen and mud, yeah.
Mud, lake bed.
Yeah.
Samples.
Yeah, lake and in marine settings. You have stuff that gets washed into marine basins, and you get stuff that gets washed into lakes, and that gives you some evidence of what kind of vegetation was around, and the vegetation might give you evidence for the type of climate that persisted for 30 or 50 or 100 years. By the same token, you can use geochemical records to get more direct evidence for either rainfall amounts, which would affect the salinity of lakes, or the salinity of the ocean, even in some extreme cases, as well as direct temperature from geochemistry proxies as well. So we have this toolkit of paleoclimate proxies that are generally used to try to reconstruct information about the past. But most of those are not available in the Caribbean. It makes it a very challenging problem to work on because you don't have the annual trees. The lakes that have been looked at, Demetrius, you know better than I do, but there hasn't been like one single like definitive lake record, right, that's come out from the Caribbean islands per se that's been like the go-to. There's been a couple that have a couple of cores from off the South American coast that have been really important, and then we don't have things like caves. Cave records are important in other parts of Central America. So a lot of the information, we look at the past and we try to infer what's occurred in the Caribbean, it's relying on an assumption that what's been happening in Central America or South America or the southern part of North America is an okay proxy, a reasonable proxy for what's been occurring in the Caribbean. That's not always the case. It's not guaranteed to be the case. It's just the best that we've been able to do up until now. So keep those caveats in mind in what I'm going to show you here. I'm not going to show myself coring a tree. That was the one and only time I cored a tree. I cored 3 trees in the time that one of the real dendroclimatologists cored 24. It's hard work. It doesn't work in the Caribbean anyway. We do have these. This is a compilation from this effort. This is called the Pages 2K. It's a consortium, volunteer consortium of paleoclimate scientists from around the world who, among other things, try to collate data and interpret and put together synthesis papers. So this is one of these synthesis papers where they looked at a whole suite of proxies that had reasonably high resolution and might be relevant to paleoclimate variations for the last 6,000 years, right? So we're going back from 2,000 years before present to 6,000 years before present. So older is on top. And you can see in the fourth one here, right? No, where is it now? No. The main feature that I want to draw your attention to, because these are global tropical proxies, is that something pretty dramatic must have been happening around the world in the tropics at about 4,000 years ago. And this has been looked at in other contexts in the Middle East, in the context of biblical stories about floods and about the Nile River and other cultures as well. There's something really big must have happened around the world in the tropics. We don't really fully understand it. It's an open problem. It's a super interesting problem. It almost certainly would have affected the Caribbean being part of the tropics as well. And it's very high magnitude and relatively abrupt. When we say relatively abrupt in a paleoclimate context, we mean a large change over the course of decades or centuries. And usually when we say relatively abrupt, we're talking about the last 10,000 years, the Holocene, the last 10,000 years until present. Anything that's abrupt and high magnitude in the Holocene is nothing. It's chump change compared to what we're looking at for the projections of the future. You have to go back much further than that, and the kinds of abrupt changes you see are a lot different. All right, so we can't make a lot of direct inferences, like I said before, about the Caribbean. We're working on it. It's a work in progress. One of the things that we can do, though, is we can look at the historical record. But again, if you look at the historical record, just to first order, you focus on the front of the room now. What might be some challenges to getting data from the Caribbean or any Caribbean-like setting over the historical period? Good. And what are the challenges to getting appropriate data looking at droughts and say, even just say the middle of the last century, from 1950 to present, a time when we definitely had high-quality station data, meteorological balloons going up. You know, we've got weather stations in some of the islands in the Caribbean because they've been of interest to the U.S. military, and yet it's still a challenge. What do you think some of the challenges? Getting data, just temperature, precipitation data, which you need to get out of. You need to have to do any kind of drought. Is that? Outliers? Yeah, so you're going to have unexpected observations that maybe were either completely spurious, someone sneezed in the rain gauge and they recorded the wrong number, or they tipped it over and they're like, I think it was about this much. Right? Okay, what else? What might we encounter in terms of a challenge to collecting data? Yeah?
Political situations.
What's that? Yeah, political situations, absolutely, right? So changes in political regimes might mean for an interval of time, there's a lot of investment and energy going into making meteorological observations, and that could persist for a decade or a couple decades, and then a new regime, and there's lack of funding, different priorities, and that's scrapped. Okay? And we want long, continuous records to say anything robust about the present context for drought. What else? Yeah, go ahead.
Maybe data is collected differently.
Right, yeah, different strategies, different countries, different protocols, absolutely. Yeah, and boy, Demetrius can tell you all about these. These are all challenges. There's another really crazy one that I hadn't thought of, but Demetrius pointed out to me when he was working on this, which was that the precipitation records, the rain gauges, sometimes will end when a storm hits, a big hurricane, just does away with that rain gauge. It's gone. That's the end of the record. So now you have to put up a new rain gauge, maybe it doesn't go to the same place, and there's the aftermath of the storm. So just getting precipitation data alone, temperature and precipitation data alone, is a real challenge, and yet we need some high-quality data sets to be able to say anything robust about the present context of drought, the 2013 to 2016 drought, and certainly the future projections of drought. So I'll talk a little bit about what Demetrius did and how he was able to work through this problem. And so rather than going directly after soil moisture, which I realize, would be a better quantity to estimate than what we're going to end up using, we have this thing called the Palmer Drought Severity Index. Has anyone come across this? Or you reasonably, if you're not familiar with it, it's obviously not expected that you should be. But think of it as just like any other index, like for the stock market. It's just it's an indicator of the relative wetness or dryness of the soils. It's not soil moisture per se, but it's a normalized index that will tell you if it's negative or more negative, it's either dry or more dry or extremely dry. And it's calibrated in such a way that a -1 or a -2 or a -3 for drought means the same thing relative to that local climate, whether or not you're in the southwest of the DR and in a relatively arid landscape, or if you're on the eastern shores of Hispaniola Island where it's a relatively wet climate. It's relative to the climate of that spot and the soil types of that spot. So it's not soil moisture per se, it's an index of soil moisture. So when I say PDSI, you just think Palmer Drought Severity Index, okay? So PDSI, you all thought it, very nice. Well done. At its core, you have a balance equation between precipitation as input and evapotranspiration, which is the withdrawals. You put it like a bank account. And Demetrius is using a slight modification of the PDSI. Good. We call these self-calibrating PDSI, which really gets at this core concept to using this index of having it be tuned to local conditions, specific to local conditions. And therefore meaning the same thing across space and through time. And that's the power of this index. All right, so here we have a previous result. This was the best that we could do before Demetrius's work. It was a product from Van der Schreier et al., published in 2013. They tied together the best data sets they could find and came up with a very coarse resolution PDSI product. And then they stopped supporting it. So it was like if you wanted to look at the 2013 to 2016 drought, first of all, you were limited to a handful of grid points. Second of all, there was no data up through the years that we wanted to study. So Demetrius wanted to drill down further and was successful in putting together a much higher resolution version of it. And this is a slide capturing why that's important. You have in the Caribbean these incredible topographic, at least from my perspective, even coming from the West, I'm from the West, and still this just blows my mind. You have topographic gradients in the Caribbean that are very impressive and very important for the local hydrology, and very important to get right if you want to have a way of assessing drought through the, say, past few decades and into the future. And in a map like this, they don't show up. They're going to be little blips. They're going to be completely smoothed down. Something like 1,000 meters over a less than 10-kilometer range, which is just nuts for trying to do hydrology. You can see that here in this map of Hispaniola Island. See some of the dry regions in here. These are climatologically drier, so you would expect them to, if you're only looking at soil moisture, have lower soil moisture values, but with the PDSI, you would expect an anomaly here to be of smaller magnitude as an anomaly here, even if they were both a -4, -3 in this PDSI metric that we're going to use. And this is an important concept for the mental model of how rainfall gets to Hispaniola Island. You have the trade winds blowing in this direction, so that inherently the eastern-facing mountains are going to always be getting more rain, right? Like almost always or always be getting more rain on average. And on the other side, you're typically going to have a rain shadow, right? And there's going to be different, obviously, agricultural applications, different types of agricultural systems are going to emerge on different sides of these mountain ranges. And the trade winds, under climate change, a big uncertainty, but any change in the trade winds would also then be expected to shift the mean climate of the Caribbean in the future, especially for islands like Hispaniola. All right, so these are all results from Dimitri's paper. And what he did is he looked at, in this very high-resolution drought atlas product, the 3 worst droughts, according to a couple different metrics, definitions of severity, magnitude, and duration that we use to query the data set. It's 4-kilometer spatial resolution. So we're able to really drill down to the point where we're able to see the topographic effects and look at this 2013 to 2016 drought in the context of these other 3. So there's one from 1974 to 1977, 1997, 1998, 2009, 2010, and then the most recent one. And so just to first order, it's a little bit more persistent than the other worst droughts. Just to first order, you can say, well, it's a little bit more persistent. And the deepness of this orange color, the richness of this orange color is a metric for the severity. And -4 and -5, that's very bad. That's extremely dry, right? That's going to have impacts on agriculture and human water resources for municipality uses and for irrigation and for, in the case of the Caribbean, hydroelectric power generation as well. -5 is very severe. And you can see it seems to be just the first order, just to my eye anyway, and Dimitrius wrote the paper, so I know that this is also accurate. It seems to be more widespread than the other big droughts that have occurred in the region. And for the most part, it was, not only was it exceptionally widespread and severe, like the other droughts, it occurred during El Nino events, right? And so El Nino is a big driver of drought in many parts of the world, including the Caribbean. And working through Dimitrius's PhD, we realized that if this was a giant landmass here instead of a bunch of islands, we would be much more concerned about El Nino's impact on this landmass and the impacts it would have on agriculture, because the impact of El Nino across the whole Caribbean region is pretty dramatic, yet it's mostly ocean, so you don't always see it, and then the impacts move around from one event to the next, or 1 month to the next, or 1 year to the next. And so if you're in an island, you might not always see it because the impact, the footprint of that bullseye of the impact is going to move around. But if this was a big landmass, we would be talking about like this being one of the core regions that's affected by El Nino variability. So just keep that in mind, especially as we think about the context of climate change, the context of the historical period for climate change. Because an El Nino drought, even the worst ones, might get you down to PDSI values of -4, -5 in the extreme case, -3 in many other of the worst cases. And an average El Nino might bring you down to maybe -2 or -3 for many of the islands, but not all the islands in the study region. Now, it got to the point, I mentioned this earlier, where Caribbean drought was, in fact, in the news. And some of the major media outlets were taking notice of the water shortages that were occurring. And as it reached its 3rd year, it was looking, I would say, pretty dire, really getting to the point where there were going to be some unprecedented types of crises if something like, if there wasn't either an intervention or if there wasn't rainfall. And it ended up being the latter. At the same time, those of you who know the California drought story, California is a country, is a state with drought problems, large-scale infrastructure, and the capacity to move water around on really impressive spatial scales. And they were pinched by a drought that coincided, wasn't necessarily from the same reason, but it coincided with much of this 2013-2016 drought. And that was in the news like every single week there was something new about the California drought and the water shortages in California. When they've gone back and looked at California, there was a big economic hit. But many of the communities, even the farming communities, that had resources were, I say, relatively unscathed. I don't mean they were unscathed. I mean that the impacts were buffered by many of the efforts and the infrastructure that's in place in California. We're talking about a drought that was probably just as bad in the Caribbean without the ability to move water around over large spatial scales, without the political and technical and physical infrastructure to manage this. And that's a, I guess in my mind, it's a stark contrast in what gets the attention of the news media. All right, obvious question. Hopefully this is already on your mind. So we had this recent drought, 2013 to 2016. And is it possible that it had something to do with anthropogenic warming, with climate change caused by human activities increasing greenhouse gases? What do you guys think? Intuition, just like yes. Who thinks like you can put your hand up and be like yes? You can like hide it from your neighbor if you want. Like yes, like I don't know, maybe, and like probably not. Not a lot of probably nots. Yes, okay. Yeah, it's this turns out to be a really hard problem. This is a really hard question to answer. And it's a hard question to answer because of the two main considerations that I've already brought up. First of all, we don't have really great constraints on the paleoclimate record, so we don't really know the natural range of variability. We don't know if the 2013 to 2016 drought was a once in a century or once in a 2-century event, right? Because even those records that we have average together multiple decades, going back thousands of years. So we don't have good constraints on the natural background rate of variability for this kind of an event. And number two, if you only look at the historical period, not only is it short, the instrumental data is problematic to work with when we're trying to pick out a long-term trend. The climate change trend is going to affect primarily temperature, definitely a significant trend in temperature over this period. Second, humidity, because temperature and humidity go together usually. You have warmer temperatures, the atmosphere can quote-unquote hold more water vapor. But that doesn't always translate into an increase or decrease in precipitation. And so, and on top of that, the data for precipitation alone are not robust enough to even answer this question. You couldn't ask this question of precipitation alone and have a meaningful answer given the records. And I want to say that again because it's really important to understand. If you were asking this about precipitation alone, you could not have a scientifically meaningful answer. We wouldn't know. It would just have to be an uncertainty. Now, with temperature playing a role in the demand for moisture by the atmosphere from the soils, we can look at this. We can investigate this, doing some numerical modeling and some statistical modeling to try to isolate the role that temperature alone, which definitely is warmer and is definitely being driven by human activities, played in exacerbating the 2013 to 2016 drought. And so that's the question that we focused on for this second or third or fifth, 10th paper that Demetrius is working on or worked on. And what we found was that it played a role. It played a significant role. It was statistically significant, but not as much as maybe some people would think to first order. And I would say these are conservative estimates, but they're very scientifically robust and reliable, and we investigated them from a large range of angles and what would be called community best practices based on 2 or 3 decades of climate change research to isolate the severity that was attributable to warmer temperatures. It's about 17% worse. So not 30, not 50%, not the main story, but certainly a factor. And even smaller contributions to the spatial extent. Both statistically significant, but relatively small contributions. Okay, so that's up till now the role that we could say in this one drought, which was bad, definitely very severe drought, climate change may have played. So does that sort of make sense? That seems clear to everyone? Any questions about this? I mean, I think these are conservative numbers, honestly. I think we could redo this a few different ways. There's ways that you could argue for a higher number, higher contribution. I don't see any way that these numbers could be lower. So I think these are on the low end. That's my professional opinion, but we haven't done all the work to say that that's peer-reviewed, quantifiable statement.
You showed a number of other years there, way back, where you began And so the question is that severity number
Mhm.
that you just put up, 17%.
Yeah.
How does it apply to 1974 or 77? In other words, is it increasing?
That's a great question. I don't know that we could actually answer it meaningfully because under about 10% for the severity and under about 5% for the spatial extent, we're in the noise, right? So if it's a 3 to 5% contribution earlier, well, maybe, but it's really hard to say. Plus, we don't have the baseline before 1950 because all those data problems, all those challenges that we ran into apply even more strongly before the 1950s, right? So we just don't know. No, we just don't know. We're doing our best. And you can see this, you can get a sense, though, I think this will answer a little bit of your question. This is for temperature for the whole Caribbean region. And the two lines here that are like lighter colors are ones from a observational product, so based on meteorological data that's been interpolated to get an average for the whole Caribbean region. And the other one is a model simulation that's given greenhouse gas concentrations and then just allowed to do all the circulations. That's just one, but many, many models averaged together to give us the trends. First of all, the trends agree very strongly. That's robust evidence that's being caused by human activity. Second of all, the temperatures are maybe half a degree warmer by the time you get to the 2000s and now past the 2000s than they would have otherwise been. And the way that we got it, how would they have otherwise been? We again looked at the model output, without using greenhouse gases as a boundary condition, changes in greenhouse gases as a boundary condition. And we did a linear detrending, like statistical experiment. So this difference is the human anthropogenic effect on temperature on average throughout the region, approximately. And that translates into 17% of the severity. Once you have a drought, it made it 17% worse. And once you had, and about 7% more widespread. The biggest factor in making it so persistent, there's no obvious role for climate change in the persistence. And correct me if I'm wrong, but I don't think we found any evidence that there was a role for climate change to have made this drought more persistent. What seemed to make it really persistent, a 3-year drought, 3.5-year drought, was that you have a initial El Nino event in 2013 that doesn't fully form into a real El Nino that we recognize, technically an El Nino, but it wasn't an impactful, dramatic El Nino like you associate with the evening news. We called it like the failed El Nino. And then it retreated to somewhat normal conditions in the Pacific, and then there was a second actual El Nino. So it's like it didn't quite start up, like your car this morning, right? It didn't quite start up, but the effect of all that variability in the tropical Pacific, which changes where the convection, changes where the rainfall occurs, and that changes where the subsidence occurs, and where the subsidence occurs for both of those events was the Caribbean. And so it was that double dip, failed El Nino with a real El Nino that accounts for the persistence, and yet there's no evidence that that would be a climate change impact. I can't say that it is or it isn't. We have no metrics at this point that I know of that would allow us to determine whether or not a failed El Nino followed by an El Nino is more probable during climate change. We just don't know. Precipitation, there's really not much we can say about precipitation. There's not an obvious significant trend in precipitation at all, and if there is, it's tiny. It's a fraction of a millimeter per decade. It's not significant either. It does look like it's decreasing. I will admit that. I'm not trying to hide this data. I mean, it does look like it's decreasing, but it's over such a short period of time in the context of such a long record that we can't say whether or not it's a statistically significant trend. All right, so now the temperature is significant, precipitation is not significant. We put them together, we get back to this thing called PDSI, and you do have a trend in the PDSI over this period towards more negative values. And here we're in this extreme drought of the 2013 to 2016 interval. It's off the charts, right? We could have drawn it differently, but could have made the chart bigger. I realized we could have made the axes bigger and it wouldn't say it was off the charts. But in the context of anything that had happened, this is a black swan, right? Like anything that had happened before this that you might use to plan for drought would not have predicted such an extreme event. And some percentage of that, 17% we say, is due to climate change. If you would adjust this line, it would actually bring it back up in line with some of the other works, the 1970s drought probably. similar magnitude. And the 1970s did have this weird El Nino roll of like a double El Nino event. If you want to look in space, statistically significant trends in PDSI for almost the entire region, and some of them are even positive, which is an interesting aspect of the work that I could get into later, and I think is very important for some of what we're expecting for the future. All right, you got 10 minutes left? Perfect. Future drought risk. All right, so this is ongoing work. This is work in progress, and of course it's led by Demetrius, and it's been, the Caribbean has received a tiny bit of attention in the context of future projections, just in passing, just in the context of other scientific studies, and so it's still an open area of inquiry. There's not a lot of literature on what we're trying to do, and some of what we're going to show might be slightly different if you ask us again in 2 years from now. So all those caveats to say, I'm pretty confident in all of this, like 91% confident in all of this. But because of the data limitations and the model uncertainties for this region and the lack of literature, there might be some slight changes if we do this again in 2 years. All right, so this is not really an exaggeration. We're going to look at global climate models to put the last 100 years, the last 50 years into context for what we could expect if things continue on their present trajectory of using the atmosphere as a dumping ground for waste CO2 from energy production. And one of the tools, maybe what's often called one of the only crystal balls into looking into the future, are these global coupled climate models, GCMs, global climate models. And here, this is a supercomputer in Wyoming. It's, I don't know, it's about halfway through its 5-year life cycle of being a cutting-edge supercomputing tool. It's 2.5 years old, so in another 2.5 years, it'll be decommissioned and replaced with another bigger, faster, more powerful supercomputer that can run more climate model simulations. This is being recorded, right? Okay. Using coal as one of the many energy sources that are available to run supercomputers. Oops, I said it. Shoot, I checked and I just couldn't stop myself. No, but they're really serious about getting wind energy to power these supercomputers now in Wyoming, which is awesome. That's fantastic. Renewables to power supercomputers to run climate model projections of the future should definitely be using renewables. I totally applaud that. Now, I didn't applaud it during the last push of Demetrius' PhD because I guess the instability or some aspects of the instability of the electrical grid combined with the complexity of a supercomputer meant that there was like a 6-week downtime hiatus, right when he's like running towards the end and we're trying to like use the supercomputer to do science, and then it's just down and it's offline for weeks. And so I was like, just use the coal. I don't know, there's people of the internet, I've said it. All right. Don't use coal to make energy in a general sense. Just when I have a PhD student trying to finish, use like a little bit of coal to keep the computer running. No. Don't use coal. Coal is bad. It's bad stuff, kills people, it's bad for the environment, causes acid rain, it's going to destroy the planet. Coal is bad. Except when it's not. Which is sometimes. So, when you look at this is the end of the century, 2081 to 2100. Middle of the summer, hottest part of the year, right? This is the middle of the boreal summer. And we're only considering precipitation in this diagram. The Caribbean pops out, and these little dots indicate significance. So there's a handful of places in the Caribbean where there is a significant drying trend from decreases in precipitation. And there's a lot of places where there's a significant drying trend, or a significant trend in getting wetter, right? And so that's not good news in light of everything we've discussed. There's potential, very significant, strong potential for a decrease in the supply of moisture. And we're very confident that there's going to be an increase in temperatures, which all other things being equal, could impose an increase in the demand for moisture. So the supply side is a real challenge if it's projected to decrease. And it's not a small decrease either. We're talking about a 50% reduction in rainfall on average across models for this whole region taken as an average. And obviously that will play out differently depending on topography and individual islands. But this is not a trivial thing to try to manage or navigate. Now, one of the only tools that is, I think, under development and has a real significant potential, at least, and we're exploring this very actively, to give stakeholders, water resource managers, farmers, growers in the Caribbean something to work with, something tangible to cope with this backdrop of potentially decreasing precipitation amounts and certainly increasing temperature and demand for moisture from the soil, is near-term, short-range forecasts. Right? So if we have a little bit of a better hold on if an El Nino event is unfolding and likely to cause another drought, and we can get a 6-month or a 9-month heads up on that, there might be more that we can do to try to manage those events as they unfold and adapt in real time to them, in addition to trying to understand the background. And that's really where my biggest interest is right now. I mean, there's a whole different field right now of investigation, of research into the climate change component and whether or not if we stay on our current trajectory, will we see a 30% or a 50% or a 65% decrease in precipitation? And how many different models do you have to run? How many different supercomputers do you need to have? And what if we use some geoengineering intervention where we spray aerosols up in the stratosphere and offset the human effects? And those are important questions. And they're like from a global policy, global climate change perspective, and they're very relevant. And however they play out are extremely relevant to what happens in the Caribbean. But no matter how they play out, better tools for forecasting on near-term timescales is something that under any outcome can be, I think, of very significant value. Of course, it needs to be done carefully, and we're not just doing this recklessly and putting out forecasts and saying, yeah, you can bet the family farm on this year being good because we've got this one model that says it will be. It's an active area of research. And central to it is an understanding of the dynamics, the physics, the circulation processes that are critical to generating drought, and how the interplay of those processes and climate change is already affecting the statistics of drought. Not just the observed part, but really like the mechanistic part. It's like the difference between, say, the phenotype and the genotype. We're trying to go after the genotype when we talk about dynamic processes that govern drought. Trying to really get under the hood at what's driving the events of the past and how those may or may not change during the future. And it's not safe to say that by the end of this century, under very extreme climate change scenario, the same processes will be occurring in the same way. That's not a safe assumption. For the next decade, it probably is not a terrible assumption. It's probably an okay assumption for the next decade. I'm going to stop soon, so why don't I just do this? I'll end here because it's such an interesting story, and it's not something that you think about. And it's one of these expect the unexpected on the road to better forecasts for the Caribbean. So we put together our best forecasts. We put together our best models. We do everything we can with the physics of drought. And then something like this happens. You get a big dusty event off the Sahel, right? And our model may or may not have good representation of dust in the Sahel. And maybe we didn't think of dust in the Sahel as being particularly relevant to drought in the Caribbean. We should have, and we do. But it's not necessarily front and center in global seasonal forecasting efforts. An important component, but not necessarily front and center. Well, it turns out when dust comes off the Sahel and makes it across the Atlantic, and it's fine particulate matter, and it stays suspended in the atmosphere for several weeks, and it gets to the Caribbean. First of all, you can see it. Demetrius has taken pictures and sent them to us when he's been doing field work of days where the Sahel air and the Sahel dust, which is it's dry air and it's dusty air, and you can see it. It's like a yellowish horizon. It's a complete difference from the mean air in the region. And it stabilizes the atmosphere. In other words, having all that dust and having it be dry makes the atmosphere unlikely to rise, to convect, and to generate precipitation. So in addition to all of those other factors that we don't have great constraints on, Sahel dust is a nightmare to deal with, for not just because it's hard to model directly. The dynamics of Sahelian dust are related to the position of the tropical easterly jet, which is itself a function of the structure of the large-scale circulations that govern the edge of the... It's like there's at least 3 different coupled subsystems that are going to determine Sahelian dust, and yet it has this big dramatic impact on the Caribbean. Now, is it doable on short seasonal time horizons? Yes, I really think it is. I think we have enough data going back over the recent past. I think we have the right model toolkit to include things like dust as well as the other dynamical processes that are important. But like I said before, it's a work in progress, and it's very urgent, and we really need to be working with people that were in this room that have a much better understanding for the types of systems that are on the ground, the types of social networks, and the way that those social networks can react and adapt to change as we experience climate change, and the possibility for introducing any forecast tools that we develop in a responsible way that doesn't cause more problems than if we just done nothing at all. So that's where we're going. That's very much active area of inquiry. It's very exciting. I'd love to answer more questions about it, but we're essentially out of time. So thank you all very much for staying awake. I mean, holy cow, you guys stayed awake for this whole thing. So impressive. Must be the beginning of the semester.